Okay. Just letting this buffer a little bit. Got it. Okay. So our goal is to understand potential energy. You want it, Alan?
I got it.
Thanks. And it turns out there's literally a lot of complicated terms that relate to this term potential energy. And I'm going to try and go through them as quickly as possible and then start doing actual problems. And so in particular, I'm just going to mention this before I start flying through crap. Pages 13, 14, and 15 kind of summarize the notes. In particular, before I do anything else, take a look at page 15 in the workbook. If he's got it there, go to page 15 really quick. That's going to be my summary. So do you see that I'm good? So we're going to talk about the summary at the end. I'm mentioning this now so that you can kind of not worry about taking a lot of notes, knowing that we're going to have this summary. Does that make sense? So I'd rather have you listening than taking notes the whole time. All right. Now, our first subset is, our first sub-step is what is conservative force. Okay. So the simple way to say it is a conservative force is a force which conserves energy. But that in itself is like, well, what do you by conserving energy? It doesn't make a lot of sense. So I'm going to try and define it in a less circular fashion. It's a force that does zero net work for any closed path is conservative. And immediately we see this sentence doesn't make any sense, right? It's crazy. So this is what I mean. There's a bunch of phrases. And again, we're going to summarize this and show you how to do problems in a minute, but I just want you to understand things the right way. So let me give an example here so that this might make more sense. Imagine we have some kind of incline, and let's say there's some friction. Okay, so we'll say mu is not 0, meaning there is friction. And let's say I have some kind of a stopper down here. And attached to this stopper, let's say, is a spring. And let's say I have a block here. All right. Now, in this case, imagine I take this block and I pull it up the hill and then back down. So this is the path. The vertical dimension, I'm not actually going to lift it up in the air, I'm just pulling it up and then bringing it back down. Everybody cool with that? All right. This is an example of a closed path. Closed path implies same initial and final position. So a closed path is one that starts and stops at the same spot. That's closed path. Got it? Now keep in mind, a force has to do 0 work for any closed path. So that means, right, I could go up this far or that far or really, really far. Any possible closed path has to do 0 net work. So notice, gotta get that word underlined too. Now, what's important to hear is only the result of this, not this discussion. So hang in there. let's think about this. Let's start with a simple force. How about gravity? Right? If we talk about, let me get that G looking a little better. If we talk about gravity, think about this. On the way up, is gravity helping me go upwards or is it opposing my forwards motion? On the way up, it's opposing it. So does gravity do positive or negative work on the way up? Negative. How about the way back down? Does gravity help me go back down? Yeah. So on the way back down, gravity does positive work. And do you agree I'm going to do the same amount of work on the way up as down, except on the way up it's positive, or sorry, on the way up it's negative, on the way down it's positive? Yeah. And that's going to be true whether I go up a little bit or a lot or somewhere in between. Gravity is conservative. It is a conservative force. This is going to be important because what it means is if you have a conservative force, instead of doing work done by gravity, we can rewrite it in terms of potential energy. So gravity is one of the forces we can stop doing all that integral crap. All right, good. How about the spring? When I pull this block up, does the spring do positive or negative work on the way up? Negative. On the way back down? Positive. And I guess you would probably believe me if I told you it's also conservative, right? So the force due to the spring is also conservative. What about friction? On the way up, which way does friction point? Not to the left exactly. You mean leftward down the plane? Yeah. Okay. How about I'll say left and down the plane? Is that better? Just because to the left would be this.
Oh no, I get what you're saying.
Yeah. So I'm just the more precise way to say that would be down the plane, but I get the idea.
Yeah.
Our displacement is up the plane. What's the work done? Positive, negative, or zero? What is it? For the work for friction on the way up, is it helping me go up the hill? So it's not positive. Is it hurting me as I go up the hill?
Negative.
Yeah, so it's negative. What about on the way down? It's hurting you both directions. Friction slows you down on the way up and on the way back. On the way down, friction's up. Displacement is down the hill. Work is negative. Is friction a conservative force? No, it does negative work on this path. And if we can find just one path where the work is non-zero, it's not conservative. The whole point of this discussion is as follows. I'm going to teach you a technique where we still need to do the work done by friction, just like chapter 7, just like last time. Got it? Only now we're going to learn a new technique called potential energy. And we're going to use this potential energy for any forces that are conservative. So we're going to rewrite gravitational work and spring work as potential energy. Got it? And it turns out it just makes it faster to do problems. Okay. So let's go over to the next board for a second. All right. So And again, you don't need to write this stuff down. If we consider every single atom in the universe and we measure its energy, and we could do that again at a later point in time, we would see that in the entire universe, the initial amount of energy equals the final amount of energy. In physics, we say if the initial equals the final, that quantity is conserved. You can conserve mass. You can have the same amount of initial and final mass. You can conserve charge. You can have the same amount of charge before and after. You can have the same amount of strangeness. That's a physics term. A lot of physicists have strangeness. But no, anyway. For us, when we say energy is conserved or conservation of energy, in physics, that does not mean turn the lights off when you don't need them. It means E initial equals E final. This seems well and good. In the entire universe, energy is conserved. But from a practical standpoint, it's not realistic to measure the energy of every single atom in the universe every time we want to do a problem, right? So we need to add one little bit to this. E initial equals E final. And then we're going to account for transfers of energy. And I'll explain what this means. Think of energy as like your bank account, right? You could have different types of bank accounts. You could have a checking account or a savings account or whatever. So you can imagine there's different types of energy you have, different types of accounts, but it's all money, okay? And then in the real world, we know that the amount of money you start with is not the amount of money you end with. And that's because there are things beyond our control, bills or paychecks, right? So you can have the work done, could be, you can think of this as energy is like your balance in your bank account. You have your savings account, your checkings account, you add them together, that's your total energy, right? And here, then you could have debits or credits. You could have energy coming in or energy leaving the system. And then you end up with some final amount of energy. So far, so good? Now for us, one type of energy is going to be kinetic energy. That's like your checking account. There's going to be another one. This is called potential energy. That's like your savings account. It's energy that you could use that has the potential to get something moving, right? And you're going to see me write this as non-conservative and external. Now, from a practical standpoint, this is going to be stuff like zombies pulling on a rope or friction, things that are outside our control. All right? All right, so the symbol U is potential energy. Now, in this case, let me tell you the types of energy we're going to have. U gravity, or U subscript G, the equation for that is going to be mgh. If you tell me the amount of mass, what planet you're on, and your height above the surface, I can tell you how much energy you have. If I did this for a spring, it's 1/2 kx squared. Okay, if you recall, K was called the spring constant. It was the stiffness of the spring. The units were newtons per meter. Does anybody recall what X was in these spring problems? The stretch or compression. So, right, here's a spring, right? The stiffness basically has to do with how tightly it's wound and what type of material and the radius of the material that was wound, right? But now you can either stretch a spring or you could either or you could compress it. Sorry, I'm having some trouble here. The spring is kind of very sharp. You compress it, right? So there's energy stored whether you compress it or stretch it. X could be either one of those things. So we say it's the amount of stretch or compression. Typically, I don't know if you remember this, there was a special thing. We assume X unstretched is equal to 0. Am I still on, Alan?
Yeah.
Okay, just barely?
Yeah, you're on the edge.
Okay, right on the edge. Remember we said something about the unstretched length of the spring? So when we're doing this spring problem like this one, right now this spring is not stretched or compressed. This is its natural state. So this value of X is always how much did it get changed from this state, right? So it's like the X, the change would be a small amount up here or down there. Okay. We'll do a picture of that later in the problem. What units are associated with energy? Does anybody remember the units for energy? Joules. And remember, 1 joule equals 1 Newton times a meter. A little sloppy, but a Newton meter and a joule are the same thing. Okay? All right. I think here we know kilograms, meters per second squared is meters, which gives you a joule. Obviously, the amount of stretch or compression would be meters, agreed? So distance. All right. So the idea is we're going to try and attack problems by saying, look, how much energy do I have? And maybe for thoroughness, does anybody remember the kinetic energy equation? Kinetic energy?
1/2 mv squared.
1/2 mv squared. Now, the final and initial, here's where that comes in. Look, we've got 3 energy terms. So instead of having a checking and a savings account, we've got checking, savings, and brokerage, or whatever you want to call it. I don't know. I'm making crap up now. But basically, we've got 1 type of kinetic energy, but 2 types of potential. Well, if you can tell me the mass G at its initial height, and the spring constant and its initial stretch, and the mass and its initial velocity, I know all of these things. I know my initial starting balances. Then you could tell me if I could do chapter 7 methods to figure out the work done by friction like we did last time, I can figure out how much it's going to change. And then I could use that to figure out something about the final state. Got it? Piece of cake. All right. If you're curious, on page 14, maybe take a look. The energy analogy is written there on page 14 for you if you want it. If you don't like that, don't worry about it. I have some pictures here kind of showing energy entering or leaving the system. If you want, we could talk about those in lab tomorrow because we're doing a lab based on this stuff tomorrow in class. I would kind of like to get to problems as fast as possible and not bore you. But there is one important thing that I want to mention. We have to be careful with this one thing. Look, if you use the potential energy due to gravity, do not do the work done by gravity. We either do work done by gravity, like we did in chapter 7, or we do chapter 8, where we do the potential energy. So you either use MGH here or MGH here, but you don't want to do it both places or you'll double count and screw up the math. Got it? Yes.
So, for example, this would be like separating the X and Y coordinate stuff. You wouldn't have to.
In some sense, yes. Yes, right? We're saying, look, the gravity is now independent from all this work calculation, right? Although, I don't know, it's not quite the same, but mathematically, I don't know. Yeah, it's not the same.
Okay.
But if that helps you think about it, it doesn't offend me too much. Yeah. In this one, right, everything's in the whole equation all the time. And the question is, do I include it here or there, just not both places? Yeah, so don't double count the gravity. All right. Yeah, all right. Go to the next page and look at the summary. Start reading page 15 while I erase the board, and I'll do the summary up here. So page 15.
You can just increase the.
And you could talk with your neighbor about it, see if there's anything you don't understand in that summary.
Yeah.
There's a lot on that page. It just takes me a minute to erase.
This one is increase. Yeah, this is increase. Accessory one. Oh, you got that. Okay.
All right. Here's the summary of all that junk. Thank you. Thank you. Good catch. Good. Let me color code this. This is the equation we're going to use over and over and over for the next 2 hours. Okay? We're going to use it in lab tomorrow. This term right here, and I think this is all on your summary, isn't it? Take a look. This should be basically the last right here in the summary. So you don't need to write it down either. It's right there for you already. The last, okay? But if you want to for practice, that's fine. This is the initial kinetic energy. These two terms are going to be the initial potential energy. Similarly, we've got U final over here. That's K final. And then here's what we're doing. We're saying, look, the initial amount of energy in these forms is equal to the final amount of energy. And then there may be a small change due to some friction or some other zombie pulling on it. So in here, we do the work done by friction. Okay, when we're getting the work done by friction, friction for us, this is not always a constant, but in general, we can say the work done by friction is F times D. Let me do it like this. Friction times displacement times cosine of some angle. Do you remember that from last time? in chapter 7 when we're getting the work done. So, okay, if we're trying to get the work done by friction in this problem, the classic thing to do is do an FBD, write force equations. Usually for these problems, it's kinetic friction because the object's actually moving, right? We're talking about objects that are bouncing around and flying all over the place. So usually what we do is you solve for N, the normal force, you know what I mean? And then friction equals mu kinetic times the normal force. And that gets us this term. Okay? So in practice, this is how you're going to do the problem. If there's friction, we do an FBD. We write the force equations, get N, sub into F equals mu N. Then we do this. When we did this part of the problem, does anybody remember what was the next step that I did? Draw a picture. Friction goes this way. Now, this is not always true, but it's almost always going to look like this. Usually, what's the angle between friction and your displacement? Usually. Okay, this is not always true, but it's almost always true, right? So at this point, you could plug in all the pieces and you could get this term. Look at how much work you have to do to get this one term. So a lot of times in these problems, we're going to say friction is negligible and get an answer that's close, but maybe not perfect. Good enough? Seems easy. Should we try a problem now? Or any questions? Oh, there's a technical note at the very bottom. I should mention this. Technically, when you lift a marker up off the ground, some people say, oh, you lifted it up off the ground, there's a new height. The marker has potential energy. Strictly speaking, that is not correct. We say the marker and the Earth share the potential energy in the gravitational field between the marker and the Earth. However, when I let go of this marker, technically the Earth does move upwards to meet it, but it's by such a small amount we could never observe it. Do you know what I'm saying? It moves like a fraction of a fraction of a fraction of a radius of a nucleon. So, okay, yes, the Earth and the marker both have the potential energy, but in practice, the marker is the only thing that we observe moving, right? Because the Earth is so massive, it's negligible. When we get to chapter 13, that's going to be important because in chapter 13, we could talk about the gravitation associated with astronomical bodies. Good? Let's do it. Take a look at problem 8.3. Let's look at 8.3. For me, it's a parabolic ramp. Right, whiteboard? Yeah, I am. Okay. We've got this parabolic ramp. There's a block up here. And I'm going to just list some assumptions. The block has negligible size. We said there's negligible friction, I think, in this problem.
Yeah, frictionless ramp.
Okay, cool. What else do we know? We know the initial height is h. So I'm going to assume the initial height of this object here. All right, so squeaky, h. Above the ground. Released from rest. So I'm just getting the important parts of the problem written down on my page. Okay. We want the max speed of the block when it hits the bottom of the ramp. Now, I'm just going to show you how I would do this problem the right way so that we're set up to do harder problems. It's overkill for this problem, but just do what I do, okay? I'm going to label this picture as stage 1. Or sometimes I call this the before picture. I'm going to try and draw a separate picture right next to it, the same size, and call this stage 2 or after. You could call this before and after, but I like stage 1 and stage 2 for reasons that will become obvious later. Try and make this thing the same height. It's pretty close. All right. Next, in all of these gravitational problems, and basically in all of your physics problems, we need a coordinate system. For an energy problem, we're going to call that the coordinate system a reference level. So let me just draw this, and I promise I'll explain it in a second. I'm going to call this my reference level. Basically, at this height, this is y equals 0. It's like the 0 level of my coordinate system. Got it? I could have chosen the top as 0, the bottom as 0. I could have chosen down here as 0. For most problems, it makes sense to choose the bottom of the problem as the 0 reference level. What do I mean by that? 0 height. So we're picking some point in the problem that has no height. And it's convenient to do that at the bottom. All right. I've got my master equation here. Oh, and wait, this block is going to be at the bottom here in this picture, isn't it? Sorry, I forgot. What's happening here? Part A, max speed of the block when it reaches the bottom of the ramp. So we're looking for the speed of this thing when it gets down here, right? I don't know what the speed is when it gets to the bottom. That's what I'm trying to figure out. I've got a before picture and an after picture, stage 1 and stage 2. Now I'm going to write my my main master equation, right? Why am I not writing the spring energy? Take a guess.
It doesn't involve anything.
There's no springs. Yeah, so I immediately can make this equation faster. If there's no springs, don't write the freaking spring energy. If it's not going up and down, don't worry about gravitational energy. Whoa. If it's never moving, you don't have to worry about kinetic, but that would be a really boring problem. All right. Okay. Now, there's something that students, want to just skip over, but I'm not going to let us do that. I'm going to do this the right way. Before we go on, I like to talk about the work. In particular, let's check if it's 0 before we assume it's 0. Is there going to be any work done by friction?
No.
No, why not? The problem said so. So that's why we read the problem. Do I need to worry about the work done by gravity? Does gravity do work? Gravity does do work. Do I need to account for it or not? I've already accounted for it. So do I need to do work done by gravity? No. It's not that gravity doesn't do work. It's that we've already counted for it there. Does that make sense? Don't double count. So we don't need to do gravity. Are there any other forces that act on a block on a plane?
The X and Y direction.
I want to go with the normal force. Okay, you're thinking, yeah, it's on an X and Y, and yeah, so we could draw, but there's a normal force. That's external. Does the normal force do any work? I heard no. Why not? It's not coming off the track. I want to point this out. Which way does the normal force point right here? Perpendicular. Jeez, I gotta want to mark it. It's moving this way. As this moves around, the normal force is always perpendicular to the direction it travels. Remember what we said last time? If the angle's 90 degrees, what's the work done? Yeah, so work done by the normal force equals 0 because normal force perpendicular to displacement. Did that make sense, what I said there? The normal force vector is perpendicular to the displacement. That's why the normal force does no work. Work done by gravity already accounted for in NGH. And finally, the work done by friction equals 0 because this problem had negligible friction. Is everybody okay that the work term is 0? And understand why? Basically, this is the first step when you analyze this equation. Before you just do the math, just do a quick check. Is it reasonable to set this work term to 0 or not? If it is, the problem's easy. If work goes to 0, what drops out? Mass is going to drop out. It won't always drop out. If there's a spring involved, the spring equation doesn't have mass in it. So problems with springs, the mass doesn't drop out. Okay. Are there any other things that we can set to 0 to save ourselves some headache? What else is equal to 0 here? V initial. Why? That's sweet. There's one other thing that's 0. What?
The final height.
Final height. We said since the block is at negligible size, right? So even though our reference level is right here at the bottom of the track, because the block is of negligible size, it's basically at 0 as well. Nice job. Cool. I'm just going to rewrite. Oh, what's the initial height for this problem? We called it H. So now instead of calling it H initial for the next step, in this problem, height initial happened to be H. Now it's a little cleaner for me to write. I'm going to cancel that mass. What do we get for V final?
Square root of 2GH.
Do I need to worry about the plus minus sign? What does V mean in this energy equation?
Speed.
Speed.
And it's a scalar in this case.
Yeah, I love it, dude. Nice. So, right, we don't need to worry about it because it's a scalar. Awesome. Okay. All right. Hey, that's the answer. If you know what H is, you know what planet you're on. We've got the speed. Feeling good? That's kind of nice, isn't it? And I slow played that one too. Okay. Now, I'm going to try and squeeze in part B right here. So I would like to erase this word reference level. Is everybody okay? I can erase that.
Yeah.
I'll keep the y equals 0 there. I'm going to draw a stage 3. I'm looking at the next part of the problem. At what height above the ground does the block have half of its max speed? Oh my gosh. Any guesses, anybody? So we know its maximum speed is square root of 2gh. That's the speed at the bottom. Here's the halfway point. Do you think at the halfway point, it will have half of its max speed? Or do you think that point will come lower or above it? Where do you think it will have half of that max speed? Down low, in the middle, or up high? I heard it down low. I heard it up high. Okay, so now we've had our guess. Hopefully this will be fun to figure out the answer. That was supposed to be it. Here's the trick. Let's pick some random spot here. And let's call this height h prime. That'll be our new height. Is it going to be moving at this height? What do you think? Yes, right? If we don't lose any energy, shouldn't it go back and forth, back and forth? I'm going to show you a simulation as soon as we get this part done, so it'll be kind of fun. So I'm going to call this V3 for the stage 3 velocity. This is why it's kind of nice to call them stage 1, 2, and 3. Because when you do that, you could just label this velocity 2. This could be velocity 1, and then it's easier to compare stages. Now, which two stages do you think we should compare to learn about stage 3? I want to understand stage 3. Which stage would be easier to compare it to? Stage 1 or stage 2, or could I use either one? Why do you say stage 2? Sure. So we know that. What about stage 1? Could we do that or not?
I wouldn't say that because it's asking, or the problem has half of its max speed, and of course stage 2 has a max or final speed which is at the bottom.
True, true.
Is it because it's moving backwards?
I'm doing this on purpose, and I'm not doing a good job, so I'm going to just tell you the answer. You can compare 1 to 3 or 2 to 3. It doesn't frickin' matter. This is what's cool about energy. You can go from here to here if you like that math, or from here to here if you like that math. Think about it. Isn't the energy here the same as the energy here? As long as the work done is 0, you can compare stage 1 to stage 17,258. It doesn't matter. I don't know. Is that good enough? Yeah.
So if there was a number there in the work done, then it would matter.
Yeah. Well, in theory, so if there's work done, there might be even more work done between stage 2 and 3. We could still do it, but we might have to recalculate this. And so if there's work done, I would pick the most recent stage. You know what I'm saying?
Okay.
But yeah, as long as you correctly account for the work, you can even go from stage 1 to stage 3 anytime you want, as long as you do it correctly. Good? Yeah. So let's do this. I like stage 1 and 3. Me personally, if something is squared and I can set it to 0, that makes my life easier. You know what I'm saying? So setting the height equal to 0 is easy, but setting the squared term to 0 is even easier. So let's do compare stage 1 to stage 3. Is everyone okay that the work is still 0 and we can just not write it?
Yeah.
Okay. Is everyone okay that the kinetic energy for stage 1 is still 0? The height for stage 1 is mgh. The work was 0, so I'm not going to write it. The kinetic energy is now V3 squared. We'll come back to what that is in a second. The height, I think I called it height prime, or you could call it height 3 if you want, whatever. Sorry, I'm using kind of mixed symbols here. What is going on in this problem? In stage 3, what were the words in the problem? The special thing that we're trying to figure out?
Half the max speed.
We want V3 equals half of V max. Do I have an equation for V max? Yeah. 1/2 of that square root of 2. Am I still on, Alan, or am I off?
It's still on.
Okay, thanks. Okay, well, look at this. The mass is going to drop out. I have something to plug in. I solve for H prime. I'll race you. Try and figure out H prime. Plug this in, do the square, cancel the mass, solve for it. I'll do it as well. I'm going to cancel the mass right now to save myself some time. Something I've learned over the years is try not to do too many steps in your head at once. That's when you end up screwing up and wasting your life. If you take just a tiny bit more time on paper, it actually ends up being faster in the long run. So I took this equation here and plugged in this piece of information. Now I can square this and not screw it up. Half squared is 1/4. This thing squared gets rid of the square root. So that's what I mean, like try not to do too much in your head. It's not that you can't do it in your head. It's that sometimes we're tired and we screw up. What else cancels now? Mass cancels. What else? G. Now, see that? It's every term now. Okay, that's cool. I guess a 2 cancels this 1/2. And then if I did my math right, H, I could bring this over. I think I get 3/4 H. Take a second, make sure you get that. Just gonna get a simulation ready, okay? What's that? Oh, you got it?
Just comparing answers.
Oh, yeah, I got you.
I didn't see the board.
Sorry, my bad. No, it's awesome. That's basically you're as fast as me. That's good. All right. Coming on there? Yeah, it is. Okay. Yep. Oh, right. Then you, yeah, no, you're right. Let me get this going here.
Said, the denominator is equal, but I'd have to multiply it by the reciprocal for whatever does not have a denominator.
Yeah. The other thing is you could just do decimals for this class, right? And just forget about fraction math and just put in a decimal for it. That's fine with me. All right. So here is an example of this problem, right? The idea is we're going to assume this girl has negligible size. And let me hit the pause button here. So in this case, the red dot that you see right here, that red dot, that's going to be, we're going to assume her size is right there. If it helps you feel better, you can imagine that the wheels are made of depleted uranium and they're a mile long running into the page. So that would be an extremely low center of mass. And then actually, let's get crazy. Let's get this dog out here. Oh yeah. We'll have a dog do this, and then we clear all my drawings. So now, remember, what was one of the first things we did in the last problem? We set a reference height. So I could choose what height I want to be 0. The top, oops, the bottom, and then why don't we make our life easy and just basically say it's right here at the bottom, right? Is everybody okay with that? And again, we're ignoring the size of the dog. All right, the dog is negligible height. If this helps, you could imagine this grid is showing us, so I could line this dog up exactly at 5. And right now, I want to point out something else. Right now, I have 0 friction, 0 friction, okay? When I do this one and run it, let's run this at normal speed. We see if there really is no friction, the dog starts out with all potential energy up at the top, all potential, all kinetic down at the bottom. If it helps, let's play this at slow motion. I'm going to do this pie chart. Now, in this case, notice when the dog gets to the top, the entire pie chart is this blue color, all potential energy. At the very bottom, right there, notice it's all kinetic energy. The dog has 0 potential energy because we're at the reference level. The red dot representing the dog's position is at the reference level. Okay. I'm going to show this as a bar chart as well. Some people like to see that. Okay, and so you can see what's happening is in an ideal world with no friction, as long as the work external is 0, the total amount of energy is not changing. We see that the energy is changing forms back and forth, but the real world is not ideal. There is friction. So let me do this. Let's put this dog over here and start over. Whoops. Oh, dog. And then just so I can see this a little better, I'm going to take away the grid. Well, maybe I'll do this. Let me just make a couple of marks real quick. So there's the starting and the ending positions. And now I can take away the grid so you can kind of see where it starts and stops, right? Now in this case, I'm going to turn up the friction and then hit play. All right, we'll do medium amount of friction. All right, and I'm going to run this at slow speed. Watch what happens to the pie chart. Notice the dog doesn't make it all the way up. This is what we see in the real world. The dog is gradually moving towards the bottom. And then just to speed this up, let's run this at normal speed for a while. The dog's getting lower and lower gradually. And we see that the energy is not disappearing necessarily. It's changing into this form called thermal energy, right? If you clap your hands and rub them, they get hot. Well, the idea is now all that kinetic energy, right, has been converted into thermal energy and it's radiating out into space and leaving the system, right? So that energy still exists. It's just changed into a form that we don't see anymore, and it's possibly being radiated off the planet and is no longer usable to us, right? You can imagine if you had an infrared camera, you could look at that and you'd probably see the wheels getting hot or the track getting hot, right? But then eventually that heats up the air around it and we don't see it anymore. So far, so good? All right, and then let's do this. Let's see, I know this is a simulation, but when we do this, let's look at the max speed. Oh, whoops, I left the friction on. Sorry, and let me get the grid so I can do this perfectly. All right, so in this case, what number should we get for the speed at the bottom? What was the formula that we discovered just a minute ago? Yeah, square root of 2gh. Well, g is about 10, right? 2 times 5 is 10. What's the square root of 10 squared? About. The square root of 10 squared is 10. You know what I mean? Sorry. Okay, so the speed should be approximately 10 down at the bottom. Let's see if our calculations match this simulation. Looks pretty close, right? Not quite, because g is not 10, it's 9.8. Looks good, right? At what point do we get half the speed? 3/4 of the height. Doesn't that dog look approximately 3/4 of the way up? 3/4 would be 15/4. It's just under 4. It looks like it's just under 4. So this obviously this is a simulation, not the real world, but it is starting to match up with our expectations. So far, so good? Yes. Okay. Let's do this. I've got another question for you. Oops, oh, whoops. I still want to keep that. Sorry. All right, let's get rid of this and this. We can bring that back. Let's get rid of this and this and this. Now we actually, let's do this. Does this let me do this? No. All right, well, we'll do it in this case. Now I want to show you some issues that can come up. Imagine we have this scenario here. In practice, well, let's start pretty low like this. Let's start with the dog very low on the track, right about here. When I run this one, we still have negligible friction. Whoa, did you see that? The dog caught air. Let's make it a little bit more dramatic. Oh boy, this is tricky. Now, what we could do is, man, what if I wanted to analyze situations where the dog remains on the track? Does anybody know how we could accommodate or analyze that? What does it mean for the dog to stay on the track? Yeah, remember what we did in the circular motion problem for the ball going over a hill? We could set the normal force to 0 and learn about the limiting speed that the ball needs to be at the top of the path. And then we could do problems based off that. And that's probably what we're going to do. What about this one? What if I wanted to put this dog in here? And let's get this, let's get the grid here. It looks like that loop is approximately 4 meters tall. Agreed? 4 meters tall. How, and it's kind of like a circle. It's not a, oh, that's kind of fun. Hadn't thought of that, but we could do that later. In this case, it kind of looks like a circle, and the radius of that circle looks like it's about 2. Where does the dog need to go to make it through the loop? For example, if I start right here, is the dog going to make it through the loop without projectiling off? No, right? Because look what's going to happen. It's going to get up here, and the dog's going to fall and magically flip it. So how high do I need to go to make this dog get through the loop? Okay, how much higher do you think? Like just barely, like that? Let's see. That didn't quite work unless you got this magic inverting dog. So notice this is the tricky thing. If we just do just higher than, or even just at that level, this is not going to successfully make it through the loop. And the reason is you lose contact, your normal force goes to 0 much earlier. If I wanted to analyze this problem and figure it out, I could attack this problem right here at the trouble spot. Give me a second. Get this grid out of the way. Pause this thing. What I could do, if I was trying to analyze this problem, I could say, do an FBD and set the normal force equal to 0 at the trouble spot. From there, I could get the speed that I need. And it turns out, does anybody remember we did this problem? Does anybody remember what that speed was? It's not your G square rooted, it's our G. We're gonna do this problem in a minute, so you don't have to look it up. I'm gonna do this with you. And then we could do an energy problem. H initial equals some question mark, and we could solve for it, right? We'd know the heights of where the dog is at the top of the loop. We could figure out the initial conditions instead of the final. Did that make any sense? And you could do this on and on and on. And then you could add in springs, and then you could add in friction, and then you could add in more than one block at once. And that's basically what we're going to do here. Do you guys want to take a break right now and then come back and do this problem? Because this problem might take us a little bit. You want to take a break? It's going to take 15 minutes to do this problem. Or should we do it? What do you want to do? Okay, let's do it. Let's do it because then it's a logical spot to take a break, and then the last half of class will be shorter. Okay. Look at the next problem in the book. 8.4. Do you see that that's where we're going to attack? And we're going to skip right to 8.4b. So forget 8.4a. We're going to skip right to 8.4b. Everybody got it?
Yep.
It's this problem that we see. You could start without me. Remember, get your side-by-side before and after pictures. Oh, wait, I need that still. I need to do this remote. Sorry. I'll get the lights. Don't forget to draw your reference level. Don't forget to do an FBD, set the normal force to 0. Gotcha. Crazy eraser. Eight point four B is what we said?
Yep.
Okay. You know what? I'm going to be lazy. I want to show you a trick. For this problem, because there's so much separation, I'm going to just label my initial height and final heights. There's so much room here. I'll call this V1 equals 0 because it was released from rest. H1 is what we're looking for. And I need a reference level. So here's my reference level. That's Y equals 0. What up, Linda?
Just bringing this back.
Oh,
Sorry to intrude.
Oh, you're good.
Oh, still the loop.
The old loop-to-loop, personal favorite.
Yeah.
I'm going to call this one V2, the velocity of the speed at the top of the loop. You could call it top, you could call it final, you could call it whatever. I chose to call it 2. That's posed just in case we need it. Let's label this as the radius. I'll call it capital R. And then I'm going to draw a separate picture for the free body diagram at the top. So I'm going to label FBD at the top. And let's start there. Somebody tell me one force acting on the block at the top. MG. Nice. Which way? I'm gonna get you a shirt that says Mr. MG. MG straight down. It works every time, right? All right. What else? Which way? I'm at the top, right? Which way is the ball pushing on the track right now? The ball pushes on the track upwards. So which way does the track push on the ball?
No.
Down. So you are right. Normal force is down. We're ignoring friction. I think it's, yeah, same. Is it?
Yeah.
Okay, negligible friction. So let me put that.
Isn't it nice having your lectures in here where you got all your toys around you?
Oh, totally. You don't have to carry stuff.
Yeah, this guy stole my classroom. This was where I was gonna teach. Now I.
Yeah, I taught over there for years too. Yeah, it's tough, right?
But yeah, you gotta think ahead, come and get a cart, you know.
It's a pain, and then it breaks halfway over. Yeah. Oh, whoops! Is this thing accelerating?
Yeah.
Which way?
Towards the center.
Yeah, towards the center of the circle. Wait, at the very top, do I have a tangential? Think about this. A tangential is changing speed, right? Right at the top. Is the height changing much right here at the top? No. So then the speed isn't changing, right? Because I'm not going up and down. So if the speed at the very top is constant for a split second, a tan is 0. So that was the trick. Do I need to worry about forces left or right? They balance, even if there are forces, right? If a tan is equal to 0, even if there were forces left, right, I don't need to worry about it. Give me a force equation. Somebody, anybody.
MG plus N is equal to AC per F. Is equal to F.
That sounds like weird seagulls doing physics up here. Anyways, all right. What are we going to do with this normal force if we want to learn about the FBD at the top? What was the point? If it's about to lose contact, we set the normal force to 0. That's a cool trick to remember. Everybody got that? What drops out if we set the normal force to 0? Okay, and not every problem is going to have the normal force drop out. Not every problem will have mass drop. But in this case, I get G equals AC. Who cares? Why does this help me with an energy problem? How does this relate to energy? What's that?
It's a material.
True, but why are we doing this problem? We're trying to figure out this height and we want to do an energy problem. What is the point of doing this FBD? What can we learn from this FBD? What's hidden inside of AC?
Velocity.
We can learn about the speed. Yeah. So what's V? Yeah, and I think I'm going to use capital R. Didn't I use capital R? Just to be consistent for this problem.
Oh, you teased this while you were doing a demonstration.
Exactly. We're doing the demonstration. We're doing all the stuff that we talked about in that demonstration and now seeing it actually worked out. Okay, so now I've got 2 stages, 1 and 2. I want to learn about this height. I know about some velocities or some speeds. What equation should I write?
MG plus
Almost there. Whoops, final. Why am I not including springs?
Springs are not
No
relevant.
springs in the problem. In this problem, is it okay to set the work to 0? Why?
There's no friction.
Okay,
I mean, gravity's accounted for.
and normal force perpendicular to displacement,
Zero.
right? So then we don't, is everybody okay that that's true? Both of these things contribute? What drops out? What does every term have in it? Mass. Rewrite. You could call this height 1. What's velocity 1? Oh, shoot, that's cool. Let's drop that out here. What's height final? 0 or not 0?
It's what we're looking for.
What is it?
Each raise up.
How high is this off the ground? So how high is this off the ground? 2R, you got it? That's the most common mistake. Now you know it. You agree it's R to the middle, 2R to the top. All right. But the speed is 0 at the top, right? No, what was the speed at the top? That's the whole point of doing this. Okay. What else is going to cancel? The G's are going to drop out. Solve for H1 so we can get to the frickin' break. We'll do the demo and go to break. I think that was worth it. We'll come back happier. Yep.
I remember something vaguely about 2R, but I can't recall right now why it's 2R, why not just R.
Well, it's because in this particular problem, we chose to set this as 0 height.
Okay. So
And
it's-
now somebody else could do the problem and set the top as 0 height, and then that's confusing because then I'd have to do, some of these people were saying stuff like H minus R's and stuff, and that,
so
I don't
it's
want to think like that.
So it's like,
It's relative to your reference level, and that's the whole point. By picking a reference level, it's easier. Go ahead.
so it would be R if we had a reference level in the middle of that.
We could do this, but then the initial height would not be H. It'd be H minus R. So unless you have a good reason to do otherwise, set the frickin' bottom of the problem as 0. Even if that means every term has a height, it's usually a lot easier to do the math for me if the bottom is 0 and then every other height is positive.
Oh, wait, I'm sorry for taking up time.
No, that's a great question. There's one exception that I'm going to show you, and it's problem 8.10. That's one where I don't set the bottom to 0. We'll do that after the break. Did everybody get 2.5R? Okay, let's see what we got here. All right, there it is. And then just to make this stand out a little bit. Just pop this in here. So you can see a little better. All right, now. The radius of this, I'm going to go from the inner to inner. It's about 44 from the inner to here, approximately. Wait, is that the radius? That's the diameter. So if the diameter is 44, the radius is 22. So what's the initial height I need? 2.5 times 22 is 55.
Oh.
55. 55. Yep, yep. Okay, so take a look. Here is 55. Now I want you to watch this thing carefully. In particular, see if it makes it through the loop or not. Did it make it? No. There's a couple of things here. Now, there's a little bit of friction in the real world, but the other more important fact here is this ball is not just rolling. I mean, sorry, it's not just sliding, it's also rolling. It's rotating, right? So imagine something like this. Something that's spinning has energy too. And so it's not, we need to add a little bit extra to account for the spinning of the ball as well as its translating. And we're going to revisit this problem in chapter 10 and do it a little bit better. It turns out, I believe the actual answer is something more like 2.7. All right. So I'm just going to try right about here and let's watch this thing go. That was pretty much it. Did you see that? And there's clearly a little bit of friction here happening. Rolling friction is slowing it down. Obviously, the sliding friction is not important, right? We talked about that, the contact force. It works. Questions? All right. Let's take our break now, and then we'll come back and we'll have some more fun. All right? If you call this fun. Nice job. I got 548 on my clock. Let's do this one. All right. So hopefully you can see this right here.
Did you try again?
Good. I think, Alan, we're back on the camera, all right? You can see this all right? Do you want to come up here, Mark? Maybe just help me out. You're the first person there all the time. I think these two pool balls down at the other end. Yep. And then don't start it yet. Then I think there's two little faint lines there on the, you see them? Right up here and here. Oh, yeah, right there. That's where yeah, that just keeps these. So hopefully you guys can all see this okay. Now, and then you're gonna want to start them about the same time, but not yet. So in this case, we're gonna have these two balls. Mark's going to release them from rest. We've got two tracks. I'm gonna call the top one, the orange one, the high road, and the bottom one, the low road, just because it goes lower. That way we can talk. So which track is gonna finish first, or will it be a tie? Is the high road gonna win? Is the low road gonna win, or is it gonna be a tie? What do you think? I hear tie. What's your reasoning? What are you thinking? Or is it just a guess?
The high road doesn't do as much, but the low road kind of gets speed when it goes down.
Yeah. Okay, that's where we wanted to go with this. So hopefully now maybe this kind of makes sense. As the ball comes in, and let me just grab one from you for a second and just hold the other one for a second. And let's just imagine this one, it's going to gain some energy, excuse me, it's going to convert some potential energy into kinetic, right? And it's going to roll across here to constant speed. This one is going to convert gravitational into kinetic, and then it's going to convert more gravitational and be going faster. Obviously, the high road is the shorter track, but the bottom one will have a higher speed, and then it's just a question of who's going to win out. All right, take your bets. Here we go. Try and start them. Ready? Ready. 1, 2, 3, go. Who wins? The low road. Watch it again. Got it? All right. 1, 2, 3, go. Clearly the low road, right? Now, we could watch this in slow-mo. It's pretty close, right? But in this case, the idea is by going lower, you gain extra speed. Now, think about it. This section of the track right here, clearly the bottom ball is going to outpace the upper ball. And hopefully, if we design this track right, it's supposed to just barely outpace it. So because it's going faster here, that's basically the difference. And it more than accommodates for the extra up and down. Which ball is going faster as it leaves the track? Which ball is going faster as it goes into the box? The same. That's the tie. Now think about it. This ball converts, it starts out here, it converts some gravitational into kinetic. It converts more gravitational into more kinetic. But then it converts some kinetic back into gravitational and slows back down. If you fall, right, these are at the same final height, the middle stage doesn't matter as long as the work is negligible, which it is. So that's why they finish at the same speed. And you can tell that by how far they launch. Let's run this one more time. And let it rip. And they both should go the same distance here. So the people on Zoom can probably see that better than us because they can slow it down and watch that. Now, let's give Mark a round of applause here. Is this always going to work? Will the low road always be faster? Yeah. Can you imagine the low road that will lose every time? I can. Let me draw one. Right? What if you had a track? What if the high road went like this? And then the low road went like this? Right? In this case, it would take so long to fall down, right? Clearly, this isn't going to work forever, right? There's an absurd limit. My question to you is, well, we know if you go a little bit lower, it definitely helps. If you go a lot lower, it doesn't help. What path will make the ball travel the fastest? Some kind of curve. Gosh, I wish there was a name for that curve. I wish I could figure out the name of that curve.
That's where.
Red curve.
The red sign over there. Do you see it?
Oh.
Gosh, if only I could figure out the name of that curve. All right, so hold on. Now, whoops. It was funny, I made students make this for me, right? I do weird things. All right, so you're right in the camera, you got it? Yeah. So this is an absurd limit, right? In the old days, there was a couple Bernoulli brothers, and one of the Bernoulli brothers figured this out. What is the path that takes the least amount of time between 2 points? It's not a straight line. I can show you that right here. The straight line path is obviously shorter. But the red ball does get down just a little bit faster in this case. So one of the brothers figured this out, and to figure it out, they had to create a new branch of mathematics that no one had ever seen before, calculus of variations. And then they challenged their brother in public, like, hey, how do you figure this out? Knowing the brother couldn't do it, basically shaming him. And that's a fun story. You could read about it. Now, for me, basically, I spend a lot of time in here with you guys. There's some things I like to do for fun. This is one of them. So this is not on the test, but it's cool. So I'm going to do it to make sure I enjoy my life. Here's another weird thing about brachistocchrones, right? Path of least time, crone, time. Check this out. I'm going to start these two balls at different spots. Which ball do you think will get to the bottom first? The top ball or the bottom ball? It's a tie. Now, you might not see it perfectly here. Maybe I didn't start it perfectly. This is another weird property. No matter where you start, you can start one right here and one right up here. In theory, they should get to the bottom at the same time. Now, we were fortunate to have a student that was really bored one time with a 3D printer. And they built one of these on a small scale that's a little bit more reliable than that one. And what they did here, they put some magnets in here. And the idea is, if I just tilt this thing, and now I could start them all at the same time by pressing these two levers, and we could see which one gets to the bottom first. And it's about the same time for all of it. So that's slightly interesting. So anyways, that was for me to enjoy my life. Thank you for letting me do that. That's the brachistochrone. All right. That's just to get us back into it. You guys ready to do some more problems? That was the fun for the day. If you're curious about that calculus of variations, read about Bernoulli and the brachistochrone.
Really? I don't know before.
Yeah, it's the same Bernoulli that did fluids and stuff. One of them, I forget which one, the Bernoulli brothers or something.
Isn't there like a Bernoulli differential equation or something?
Yes, and we'll do it in chapter 14.
Yeah.
Yeah, the Bernoulli equation, that same, I don't remember which Bernoulli was which. Is it the Bernoulli that was making fun of the other one or not? Yeah, I don't know, but it's kind of interesting to read. If I find the article or something, I'll send it to you. I hope I'm not making that up and just been told a lie, but yeah. All right. We haven't done anything with springs yet. Let's do, let's look at 8.10. Oh, those crazy Bernoullis. Now, I know in your workbook, it only shows 2 stages. I'm gonna draw this as a 3-stage problem. We're gonna have a block here at rest. It'll land on some spring. So we should attach that spring. In this case, the block is moving. And then we're going to have this block land on this spring. And we're going to reach what's called max compression. Okay, and I want to explain some of the terms that you're going to see in spring problems. I'm going to bring up a spring just so we have it. You can imagine this is not a very good simulation of it, but here it is. This is the block. It's going to come down and it's going to be moving just before impact. Then it's going to collide and compress the spring downwards. What would happen next? If we're at max compression, what's the next thing that it would do? It would go back up. So something special about this that you just pointed out. The block is reversing direction at max compression. You agree? What is your speed at max compression? 0. If you're reversing direction, that's your, right? Just like when you throw a ball up in the air at max height, it reverses direction. Velocity was 0 in the y direction. Outstanding. And I'm going to call that V3 because I'm calling this stage 3. Is everybody okay here?
Yeah.
So speed 3 is 0. Is the speed going to remain 0 or is it going to change?
Just after stage 3.
Just after stage 3.
It's going to change.
It's going to change. So if the speed is going to change, is there acceleration? Yes. A is not 0. Oh man, this red marker is nice. Where have you been all my class? Oh, I love it. Let me ask you this. Is there going to be force? Or is the force equal to 0? What do you think? Is the spring squeezed?
Yes.
Will there be a force?
Yes.
Yeah. Now you might be saying, well, wait, mg balances, doesn't it? No. In this case, which way is this block going to accelerate? Upwards. So think about this. Think very briefly. There's a spring force up. There's an mg down. And this thing is going to accelerate upwards. Which force is bigger? Exactly. So the net force is not 0. So students want to attack this problem, and sometimes they want to use, oh, I know the force due to a spring is kx. That's true, but I don't know the acceleration, so this doesn't help me do a problem. Did that make any sense? We do not want to do forces for this spring problem because I don't know the acceleration. I don't want to figure it out. I probably could, but I don't want to. But we do know the speed is 0. This is a sign that maybe an energy problem is useful. Whenever you see a spring changing size, think energy. See if you could solve the problem. Got that? Now I'm going to list a couple of assumptions. Okay. Air resistance is is negligible, just so we don't have to worry about that. And how about I have no energy lost during impact? Not exactly true, but one of the points of using a spring, this is one of the reasons we use springs. It's to reduce the amount of energy loss during an impact, right? There's springs on your bumper so that your car doesn't get crumpled. So yeah, or on the shocks, right? So when you hit a bump, we're not damaging things and losing energy. One of the points of the springs is to try and reduce the energy loss during an impact. So we're going to assume that's negligible for this problem. We'll learn more about energy loss during impact in chapter 9. Okay, ready? I'm going to write an energy problem for this. I should read the problem. I don't even know what we're trying to do. Do you? Part B. Oh, we did part A already. Do you agree?
Yeah.
We were talking about what stuff is zero velocity, acceleration, or net force. So part B. We know the spring compresses a maximum amount X. Determine the spring constant. Okay. So in this case, we're told this distance right here is X. We're doing an energy problem. What's the next thing that I should do? And maybe I'll make this clear. This is the floor, so I'll draw some shading just so it looks a little better. Sorry. That's the floor. What's something we've done in all of the other energy problems right after we draw our pictures?
Reference.
Reference level. What is the usual reference level we have used? The bottom. Let's learn this technique. Let's set our reference level right here. That way we know how to handle this. And that way, if you're worried about like, oh, what about forces X on, blah, 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 blah. Well, at this point, do you agree X on is still 0? The unstretched length of the spring is still 0. So now if we did want to use forces, we wouldn't be doing strange math. We wouldn't have to redo the problem. In this problem, I think they said the initial height is h. Is that right? Okay. In this problem, we might have gravity, gravitational energy, we might have spring energy, and we might have kinetic. So we got all three. What about work done? Do we need to worry about work done? What do you think? No, that was the point of these comments up here. We are assuming okay. Obviously, there is a force between the block and the spring, but that's internal to the spring block system, right? The force between the block and the spring and the platform is internal. Does negative work on the block, positive work on the, okay. Okay, which stages do you want to compare? 1 and 2, then 2 and 3, or what?
Probably 2 and 3.
Nope. 1 and 3, because I don't know the speed yet. And we could do 1 to 2, then 2 to 3. But because work is 0, I'm just going to go straight from 1 to 3. And then I don't even need this picture, which is why I didn't draw it in the book. But I feel like this helps you understand the problem. And good enough? Yeah. Okay. mg height 1 plus 1/2 mv1 squared plus 1/2 kx1 squared plus work, which we said goes to 0, equals 1/2. Whoops. Let me try and write them in the same order. I'll get out of the way. Put a box around this. Okay, there's our energy equation. The next thing that we always do, plug in stuff that's zero. Tell me anything that is zero in stage one.
V3.
What's that?
V3.
Okay, V3 is zero. All right, I'll go with that. Give me something else that's zero.
V1.
Oh yeah, was it released from rest here? So it was dropped, AKA released from rest. Excellent. What else? X1, do you agree the spring is not yet engaged? So the spring is still unstretched? Remember, X here is not the length of the spring. It's the amount the spring has been squished. So it hasn't been squished yet or stretched. All right, so now I'm going to rewrite this. On this side, we get mg. What's the height I should use for stage one? Is it x? Is it h plus x? What do you think?
H.
It's h. This is where we called zero. So let's label it on this side too. So I'm only h, so I'm going to do mgh. I think that's it on this side. What's height 3?
H. Right.
Negative x, right? Heights above this level are positive, heights below it are negative. So I should write mg negative x. So that's what happens if we don't choose the bottom of the problem as zero. Sometimes we get negative heights. That's not a problem. We have some negative energy. So what? Only changes in energy matter. So later on, we'll realize, I don't know if you could see this, there's an initial and a final. We could rewrite this equation as a change in energy, and only changes in energy are physically meaningful, not whether a number is positive or negative. Okay. And then what's x3? X. And here, it's going to be x squared. Now remember, in this one, x is a positive number always. And it's squared anyway, so who cares? But x is distance, it was compressed. So a distance is always positive, but this is a height. That depends on the coordinates. Subtle difference. Understood? X always positive. H could be positive or negative depending on reference level. Do you agree the mass does not drop out in this one? And then if we could solve for something, great. I don't care at that point. It's easy, right? What are we supposed to solve for anyways? K. All right, good. So to solve for K, it's pretty easy. Which thing is a little bit harder? Look at part C, the challenge. Why is solving for X a little bit harder? Yeah, it's a quadratic. So you could do a quadratic formula to solve for X, agreed? And everybody would love it, but it'd be a big man. It's not that hard. It's just find A, B, and C in the quadratic formula, shove them in, and say, that's a really ugly equation, but I did it. All right. I did it for you if you want to know. Feeling good? There's some other good problems here. I want to look at, I'm going to look at 8.19. Okay. Oh, wait, 8.19 is frictionless. Let's do 8.18. I'm sorry, 8.18. Sorry about that. I'm going to draw a blue block and a red block. And I think of the solutions, I may have accidentally done red and green, so if so, I'm sorry if this doesn't match perfectly. I know that looks kind of crappy, but whatever. I'm gonna call this stage 1. And over here, the red block is almost to the ground. Just before impact, and I promise I'll get out of the way. My picture's not that great, but it gets the job done. Okay. I want to try and talk about 2 block systems. So then there's some little issues that come up when we have 2 blocks. And also this one I think has friction. Is that correct? I think that was why I picked it, right?
Yep.
It says mu kinetic equals 3. And so this is mass 2m. This has mass m. And mu kinetic was 0.3, I think. And based off last week's lab, I think, oh, by the way, I have your labs graded. I forgot to tell you earlier, class. If you want to talk to me afterwards, or just get them tomorrow, whatever. You saw these coefficients of friction are crazy all over the place. Now we know why they're always only putting 1 sig fig on them, because like beyond that, who cares? It's going to reach the ground with impact speed v. Okay, so this one, we're told that this one reaches with some impact speed v. And the question is asking about the height. All right. Here's the trick I want to teach you on this type of problem. When you have 2 blocks, use 2 reference levels instead of 1. Okay? In the previous problem, we always said, let's make this reference level. Well, what I'm going to do is I'm going to have a reference level for red. This is going to be some height above the ground, and I think that's what we're looking for. That's WTF. I don't know the height, but I do know this, so I'm going to try and figure out the height. Now I'm going to set a separate reference level for number 2. Why am I doing this? Now I don't have to try and figure out what's the size, does it matter, who cares? I just told you a second ago, the only thing that matters in these problems is change in gravitational energy, right? That's what, there's always an initial and a final, so there's always a delta U in all of these problems. In this case, right, what we want to do is we set this reference level to 0, and then I don't have to worry about the gravitational energy associated with 2m at all, right? Okay. Is there going to be work done in this problem? Yes. How do we get the work done? Let's start with that, because that's the annoying part. How do I get the work done? What's doing the work in this problem? Friction. Friction is going to be a constant force. It's going to be F times displacement times cosine of some angle, right? Draw a picture. Which way is the friction in this problem? That way, because right, 2m is the one with the friction. So here's friction. Which way is it being displaced? To the right. What's the angle? 180. What's cosine of 180? -1. -1. How do I get the frictional force? What's the technique for learning about a force that we did for 2 chapters in a row? Okay, 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 okay. Well, how do I get the normal force? FBD. Tell me one force acting on block 2M. mg. Well, in this case, it's 2 mg. Yeah. Ooh, we're living on the edge now. Whoa. What's another force acting on the block? Normal force. Which way in this problem? Straight up? Okay, cool. What else? Tension. What else?
Friction.
So let's throw that in green because I've kind of been doing that. Is it accelerating? Which way? Cool. Well, what's the normal force for this particular problem? N is 2 mg. Do you agree we don't actually need to do all the work this time? We could just see, because there's no acceleration in the vertical direction, the ups equal to the downs. So tell me, what's my equation for the frictional force? After all is said and done.
0.3 times.
Yep. So I'm going to just write it as, whoops. Can I just write 2 mu kinetic mg? Are you okay with that? So in this case, yeah, there's a 0.3. I think he said there's the 2, and so it would be 0.6 mg. Yes.
If the tension would not be horizontal, but like an angle, then you would have to do.
If the tension was at an angle, we'd have to first do the forces in the y and the x, and then do some thinking and eliminate the tension. And yes, yes, you're absolutely right. So basically, if he's saying if the tension was at an angle, what would I do? All the crap that we did in chapter 6. You know what I'm saying?
Plug that into another.
Yes. You'd write an equation in the x, use that equation to eliminate the equation. It would be a mess. Ugh. So that would be a harder problem. All right. Do we know the work done now? What's the work? Is this the work done? No, that's the force. We got to plug it in. What's the work done by the friction? No, we're looking at block 2, right? Right? We know friction points this way, it's displaced this way, there's work done. We don't worry about the work done by gravity on this one, because we're going to account for that. Remember, we're going to do gravity as an energy, so we don't have to do the work done by gravity. We only need the work done by friction here. What's the final answer for it? Negative from the angle to mu kinetic mgd.
Or negative 0.6 mgd.
Negative 0.6 mgd. Now, this seems really stupid, but when I'm doing work done by friction, I think about Miller genuine draft. And it helps me remember there should be a D there, because what's going to happen is you're going to forget that there's a distance. You're going to do all this effort to figure out the force. And then I just think about work. It's like MGDs, right? The more work I do, the more MGDs I need. Okay. If that works for you, great. If it doesn't, whatever. You guys probably don't even drink, right? Sure. Okay. Next, we have figured out the work done. Let's do our energy equation. Ready? We got time. Oh boy. It's going to be a long one, right? I've got M2 G height 2 initial plus 1/2 M2 V2 initial squared. Do I have any springs?
Nope.
Sweet. So that means I can just go over here. I've got M1 G H1 initial plus 1/2 M1 V1 initial squared. So there's my two energy terms for 1. There's my two energy terms for 2. I've got plus the work done by friction, which will be negative when I plug it in. I'm losing energy. Equals, oh boy. You get the idea? I'll get out of the way. Give me a second. It looks horrible, doesn't it?
Since we're plugging this in for the work, what does MG relate to? Or M, excuse me.
Give me just a second.
Okay.
Yeah, sorry. It's a good question. I just want to make sure I'm not screwing this up. We still on, Alan?
Yeah.
Just barely?
You still got like a patch next to it.
Okay, I'm gonna zoom it back in just a little bit then. Go this way. That's probably about as good as I could get. All right. Okay, so Mark, what were you saying now? You were asking about M's or something?
Yeah, for the work, because notice how we just wrote down as
The 2M came from right here.
Right.
So M, I guess basically in this problem, you agree that M2 is equal to 2M
okay, fair. Oh, right.
and
that's what it was.
M1. Sorry, I didn't say that. I did a bad job. Does that help?
Yeah, got it.
Anywhere I see an M1, I just put an M. Anywhere I see an M2, I'm gonna put a 2M.
Okay, got it.
Does
Thank
that
you.
help?
Yeah.
Now, you may be saying, this seems really silly, but I don't know if you can see it. When I plug all that crap in, what's gonna drop out? What is every single term gonna have in it, including the work?
Okay.
M, that's why I'm doing it this way. Is that cool?
Yeah, got it. Thank you.
All right. Now, we do not want to write all this over and over. Do you see how critical it is to plug in anything that's equal to 0 first? Give me anything that's equal to 0 right now. And why? What's that?
Y2, 0.
Oh, sorry, you guys are doing a great job, but I heard two things at once. I couldn't make sense of it. But what were you saying?
So Y2, 0.
Y2. Oh, yeah. Any of these heights for number 2 are 0. Is that what you were saying too?
I'll say something about V3, but I think I'm in the wrong way.
Yeah, we're looking at this one, right? Okay, so do you agree, basically, the whole point in setting the two reference levels was to mean I don't have to do that. With experience, you would not even write this down. Do you agree? Because if you know it's not going to appear, don't waste your time writing it. If you're learning and you're still bad at it, like most of you, write it down and then set it to 0 until you feel good. Okay? What other terms are 0? For 1 or 2?
Each one.
Yes, H1 final is also 0. Agreed? Was this thing released from rest?
Yep.
Sweet. Why? Why is that useful?
The initial of one answer.
Okay, yeah, so that means this is going to 0. And this one, the initials are 0, agreed?
Yep.
Anything else? Do I know the final velocity of 1 in this problem? Is that what we were told? Was that a given?
We were told it has some impact.
Yeah, so that's a given. Okay, and we're looking for H, right? So I'm looking for this term. This is known. What about this term? What's the speed of number 2? I know that this block is moving with speed v, but what's the speed of this block? V. Why?
They're both
Connected.
They're tied together with the string. They're probably moving the same speed. Nice. So there's a little bit of a trick here. You're supposed to know, oh, the problem told me this is V, and then I know this is also V because they're tied together with the string and they're moving at the same rate. So even though this looks like it was going to be the worst day of your life, it's only the second worst day of your life. It's great. Okay, what's M1? M, G, H. This is what we're trying to find. Keep an eye on the prize. What was the work done by friction?
2 UK.
No,
Negative.
negative. That negative matters. You were close. You agree?
Yeah.
Negative 2 mu K MGDs. All right. This is 0. What do I get on this side? This red term becomes what's this term?
And 2.
What is M2? 2M. So we see, even though they have the same speed, they don't have the same energy because this one has twice the mass. What does every term have in it? And this is why we do that, Mark. So rather than calling them 1 and 2 all the time, I know that I'm going to put in M and 2M and the mass will drop out. Okay, beat me to the punch. What are we solving for? H, get it done.
I was also confused because I didn't consider that. I don't know. I just forgot about like calculating the rest. I was like,
But
oh,
you're good now?
yeah.
All right, who cares? You got it. Ooh, look at this, everybody. Check this out. This, you might like this. I'm going to divide every term by G right now. That way, I've got the parameter that I'm looking for. See that? Now I've isolated H almost. I get a G dropping here. I get a minus 2 mu KD equals V squared over 2G plus V squared over G, which that's going to be 3 halves V squared over G. Excuse me. What do you think? What's something I could do at this moment to check this answer is right before I keep going? Check the units. What are the units of H?
Meters.
What are the units of this? What are mu? Unitless times meters. Looking good. How about this? Meter. Oh boy, I gotta write this one out because I don't want to screw it up. I'm pretty sure it's right, but let's check it. Meters squared per second squared, and then I'm going to multiply by the reciprocal of those units. G has units of meters per second squared, so that's second squared over meters. Looks like we get meters, right? Okay, so I'm feeling pretty good. Now I finished my algebra. You know what I'm saying? H equals some crap. Got it. H is equal to 3 halves or 3V squared over 2G plus 2 mu kinetic D. Weird, right? Imagine you could make these problems infinitely hard, just adding more and more blocks, but you could do this. This is a standard procedure. This is what we do in every single problem. Cool, right? I know it's time to go, but we've got just enough time. I want to show you 2 other geometry tricks. And I think at least one of them is used in tomorrow's lab. If you have to go, I'm not offended. I want to make sure this is on the recording. If you do have to go, I want to point out that at the bottom of page 19 is the summary for everything we've done. till now. So if you want to look at that summary right now while I'm erasing the board, I recommend it. Page 19 at the bottom. And I'm just going to talk about that summary and two weird geometry things, and we're out of here. Okay. You like that, don't you? It's fine. Okay, don't think too much. Look at this. Geometry tips, 1. This is one of the problems we haven't yet done, but there's going to be some in the homework like this. If this ramp has length L, what's a good way to express this height in terms of L and theta? So for inclines, the heights are going to relate to L sine theta instead of Y. Everybody got that? That's one of the things. This one's a little bit harder. We're going to have balls on a string here. Right, a pendulum. Now look, I don't want to spend all day on this. I'm just going to walk you through it. You got it in your notes. You're going to do it tomorrow in lab, but just look at this. Here's the height that I care about, H. If the length of this side is L, and this angle's theta, what's the length of this side? L sine or L cos?
L cos.
Now, hear me out. This length is L, right? Just watch my fingers here. If this length is L, what's this length? Yeah, so this whole thing, L cos plus H, is also L. Do you agree that L equals L cosine theta plus H? So H is equal to L times 1 minus cosine theta. This appears in a lot of problems. It's just two different ways. Basically, this is the only stuff we hadn't covered yet. How to get heights for an incline or how to get heights for a swinging pendulum. Got it? It's in your notes. It's in that summary. The rest of the stuff, let's read it really quick and get you out of here. Number 1, before doing conservation of energy, think. Do I have to do work for friction or work due to a zombie pulling on a rope? Number 2, forces pointing towards the center of circuit of motion do no work. Here's an example. How much work is done by the tension in the strain? 0, because the ball is being pulled towards the center. It's perpendicular to displacement, right? All right, so just like the normal force, right? Did no work on that one. In general, forces perpendicular to displacement do no work. For a 2-block system, give each block its own reference level. We saw that internal, oh, I forgot to mention that on this problem right here. Let's just look at it while it's up really quick, because I've got it. What about the work done by tension? Why didn't we worry about the work done by tension in the strain? It's internal. It's doing negative work on this block, positive work on that block. Did that make sense? Internal forces, we can ignore the, right? We talked about that once, I think. If not, I forgot.
Here you have the rotating coordinate axis would be.
Yeah. If you have the rotating coordinate axis, you can really see T is internal, right? Okay. For pendulums, use that picture over there. And for basically the last little bits of these, get out of here. All right. Basically, for inclines, use this. For pendulums, use this. Got it? Thanks for the extra time. Woo! That was intense. Make sure you bring a dog on a skateboard to lab. That's a joke.